is handling by Dr. Manoj Kumar B. He is a scientist at Advanced Systems Laboratory, Hyderabad of DRDO organization, India. He is also working as an adjunct faculty in the Department of Mechanical and Aerospace Engineering at IIT Hyderabad. He received his BSc Engineering from RAC Rourkela, MTech and PhD from IIT Madras. He also completed PGDFA from the Institute of Chartered Financial Analysts of India, Hyderabad. Dr. Burgoyne has well over the 2 decades of hands-on experience in the design and development of composite products. His primary research includes the fields of filament winding, tape winding, rosette layup, and contact layup techniques. His major contributions have been in large-size composite pressure vessels, grid-stiffened composite structures, tubular structures, ablative liners, and composite rotor blades. He has several journal and conference publications to his credit, and he is also the life member of Indian Society for Advancement of Materials and Process Engineering. He is also the life member of Aeronautical Society of India. His contribution to the field of composites have been well recognized, and he was awarded the Laboratory Scientist of the Year by DRDO and National Science Day Commendation Certificate and Silicon Medal, along with the Performance Excellence as a team member, Agni Award for Excellence in Self-Reliance as a team member. Now, currently he is working with the innovations on AI in the composite technologies. We are very glad with the brief biodata of the Manoj Kumar B, and we are lucky to have such eminent personality from DRDO. Over to you, sir. Thank you for accepting our request.
Yeah, thank you so much for your kind introduction. I'm humbled actually, but in any case, okay, I am very happy to be associated with QIS College of Engineering Technology, Angol. Professor Sami was in touch with me, and when he requested for a talk, I said, all right, very good, because I always enjoy being associated with academic institutes. Anyway, if I can go ahead right now, okay, I would say that my topic, whatever I have chosen for today's presentation, is on composites. And composites, especially in mechanical engineering. But before I proceed any further, let me also have a kind of disclaimer that I am not a mechanical engineer. I actually am a civil engineer. Then I have done my master's and PhD from aerospace engineering, where I studied, I learned composites, but I have been working in mechanical engineering field. Okay, for the past about 3 decades. That's how I felt that all right, I would be able to do some justice, hopefully. Okay. Well, before we go ahead, we always should ask a few questions. Okay, now when we are talking about composites, let us address why composites. For that matter, anyway, okay, in whatever field, okay, a kind of characteristic feature of human civilization has been a persistent quest for better products, and there composites have helped. And when you talk about composites, composites can be addressed from 2 major angles. First one is a kind of work in specialized fields, okay, maybe in mechanics and analysis, manufacturing, materials and testing. These are some fields or areas where possibly we can work in closed compartments. Without, let's say, if I'm working in mechanics, I possibly may say that, okay, I don't need to worry much about manufacturing. I can afford to, work in closed compartments. And the other one is product development, where we'll see a little while later that it is basically design, where the same fields, that is mechanics and analysis, materials, manufacturing and testing, all these fields will have to be addressed in closed connections, or the closed compartments are closed now and closed connections have to be established, and a kind of integrated approach has to be adopted. Today's discussion will be mainly in the right hand side, whatever I have shown here, that is in respect of this product development in an integrated manner. Well, before we go any further, let us again address, and know that composites are used today in a variety of applications. I'm not going to read out all of these. All these applications are there in various fields, starting with aerospace, automotive, chemical industry, civil, and so on and so forth. The list goes on. And based on this, let us know the scope of and content for this presentation is basically twofold. First, again, a brief note on composites where we will discuss or address these four domain areas. And we also, keeping in view the subject or core area of the faculty development program, that is how to go about the next mechanical engineering, that how we move forward, especially by using AI. But mind you, again, I am not going to discuss about how AI can be adopted or applied. I'm no expert in AI, but I'm only going to talk about some sort of possibilities that can help us go forward or do innovations, do better things using AI. Well, a few of the things will be very, very brief, very, very primitive. For example, the definition of composites. I actually do not know the background or the composition of the audience, so I just thought that some of the things can be very elementary and some others probably would be a little bit advanced. Okay, so composites are a kind of multi-phase materials. One of the phases is basically reinforcement and other one is matrix. For that matter, whenever we talk about any structure, we can have some a structure can be considered as be composed of some plates like this or a shell like this. And if you take a very small portion of it, small elements, then if it is a composite, then we will have a kind of reinforcement, something like this, which is a discontinuous phase, and basically it is the load bearing phase. And the other one is the matrix, which gives us the shape of the material or the structure, and it binds the reinforcement. And in the definition of composites, we must note that there are three key aspects. First one is, as I just mentioned, it is the multi-phase material, matrix, reinforcement, and the interface between the two. And the second one is that the combination is at the macro level, that do not react chemically and they do not lose their individual identities. For example, in this particular figure or whatever you can see, this is something like this, a resin. This is a reinforcement, some fabric. But when you combine, you will get some components, some product like this, where the individual fibers do, or the resin, they do retain their individual characteristics. But as a whole, when it comes to the final product, it gives us better engineering properties. Well, another very important point that I have actually realized after 3 decades of my experience is that whenever we talk about product development, we must know where we stand. And when you look around us, the materials around us are of basically 4 types: the metals, the ceramics, the polymers, and composites. Composites can have 3 basic matrix materials, either metal or ceramic or polymer, and accordingly we have got metal matrix composites, ceramic matrix composites, carbon-carbon composites, and polymer matrix composites. Okay, and again, depending on the form or physical shape of the reinforcements, the composites can be either isotropic, unidirectional, bidirectional, 3-dimensional, and they can be particulate, short fiber, flakes, or if they can be laminated composite, sandwich, etc. Our discussion today will specifically be focused on these laminated composites. And when we design any composite products, we must know what exactly we are doing the design with. For example, if we are doing a design using some flake composites, then the mechanics procedures or the design methodologies would not exactly be valid. That would have been otherwise valid for laminated composites. That must be kept in mind. Well, what is a composite product? Composite product is basically, I would say, it would have some laminate. we'll come to the definition of laminate. Okay, you can see what a laminate is. Basically, it's something like this. It comprises of a number of plies or laminae, and there are some metallic parts or other elements like a bracket or fittings, etc. And obviously, there will be some joint. This is a very, very basic elementary definition. And another point that can be seen here is that the composites, normally in a composite product, would be a predominant part, and the manufacturing methodology also will possibly be predominantly one. For example, we'll see later on that there are different processing methods. Manufacturing methods can be different. For example, a composite product can be either filament wound, but there will be some secondary methods as well, like layup, curing, etc. Or it can be compression molded. Again, there can be some secondary methods like machining, curing, etc., and so on. Now, when we talk about product design and product development, this is something that I would like all of us to be focused at. Okay? Now, product development can be considered as product design and its translation. That is, or in other words, we can consider product design as a notional development. That means in our mind, we basically take care of the development of the entire product till the final acceptance and qualification. That would consider, or that would involve considerations of all these four domains that I had mentioned before. And once I have done the design, the product design or the notional product development, finally I have to translate it physically to a real product. Now today we will be discussing about this particular portion minus this translation. It is important to note that an integrated approach is essential if we have to do a design of a product successfully. Well, the first part is the materials, and out of the two basic phases, reinforcement is the first one, and from a mechanical engineering point of view, the three very important aspects to be addressed here are that what are the common reinforcements that are available while making a composite product. Okay, the reinforcements can be something like carbon fiber, can be glass fiber, aramid. There are other fibers like natural fibers, bamboo, basalt, etc., or boron, and so on. Okay, but most mechanical engineering products are made by using carbon fiber, glass fibers, and aramid fibers, out of which glass fiber is mostly used in most of the common commercial applications, whereas carbon fiber and aramid fiber, Kevlar, etc., are used in high performance aerospace and other applications. Okay. Again, in carbon fibers, there are different types like pan-based carbon fiber, pitch-based carbon fiber, rayon-based carbon fibers, etc. That they are classified basically depending on the precursor materials. Okay. Similarly, glass fibers can be E-glass, S-glass, etc. They basically depend on the composition. And aramid fibers, the Kevlar, Nomex, etc. basically brand names. And a very important point to be noted here, especially from the shop floor fabricational point of view, are what are the physical forms that the fibers are available in. They can be continuous, short fibers, fabrics and mats, and ready-to-use materials and preforms. Continuous fibers can be strands, okay, because these are very fine filaments. In a strand, this term strand normally is applicable in the case of glass, where about 254 filaments would form a strand. In the case of tows, it is basically applicable in Kevlar and carbon, where in one tow there can be some 3,000, 6,000, 12,000, or 24,000 filaments, and depending on that, a tow can be referred to as 3K, 6K, 12K, and so on. A roving, again, a collection of a few strands. Yarn, a strand when you basically twist it, then it becomes yarn, twisted yarn. Tape is another form. These are all continuous forms. Okay. Short fibers are basically if you cut a strand to number of small pieces, like about say 10 to 25 millimeter, that kind of size, that would become a short fiber. Particulate fibers are also short, short basically, and that's another form. And fabrics and mats are basically obtained by weaving the rovings in strands and yarns. They can be woven or non-woven. They can be unidirectional or bidirectional. CSM, surface mat, etc. are non-woven forms of reinforcement. Then you've got these molding compounds, and a very, very important form is the preforms, where dry reinforcements are formed to some physical shapes. Okay, and that would be used in some other specific fabricational methods. Okay. And typical properties can be either physical properties like density, text, surface density, etc. The mechanical properties like tensile strength and modulus, thermal properties like expansion, conductivity, etc. And again, we also should know some bit of, overall idea. We must have some overall idea of what kind of properties a particular fiber can have. For example, carbon fiber can have a very wide variation in the tensile strength and modulus, but density is normally reasonably close. Okay, they vary in a close band. Similar is the case with matrix materials. Here also we should know the common resins, the physical forms and typical properties. Epoxy, polyester, and phenolics are some of the very, very common resin systems. They can be thermoset and thermoplastics. Epoxy is mostly used in high performance applications, polyester in commercial applications, phenolic mostly in some thermal applications, and so on. Well, I would not like to spend much time on the details, but I just felt that, okay, we should know how to move forward. And there are many aspects in respect of innovations, but today I just felt that we should, or let us just have some discussion on how we can use AI, okay, in the composites. Okay, in the case of materials, AI can basically be used at least in two different ways. One is the material property prediction, and thereby in selection of materials in during design. The basic properties, that is the properties at the sample level and the properties at the product level. These two terms should be differentiated. Okay, I would come to these product level properties a little later on. And the another one is that, okay, we need to develop new materials. And when it comes to material development, material design, especially in composite material design, is a very important aspect, and AI can make a lot of difference. And as a matter of fact, a lot of research work is going on in this field, that is the design of new composite or design of new materials. Well, the next area is mechanics of laminated composites. Okay. Now let's have a look at how we define a laminate, or first a lamina. A lamina, as you can see here, sorry, let me just change the pointer. Okay. A lamina is basically a single sheet of a composite layer. There can be two basic coordinates. One is the global coordinate x, y, z. The other one is the local coordinate 1, 2, 3 coordinate systems. Okay. Now, the plies can be oriented in different directions, as you can see here. So the local coordinates for each ply is different or can be different, whereas the global coordinate is the same for a particular laminate. Okay, and all this put together, what we get is a laminate. A laminate can be a flat panel, or it's a plate, or it can be a shell. Okay, and when it comes to the composite mechanics, by the way, I'm trying to avoid any, because I don't have any means to cover the entire solid mechanics here, or the total gamut of mechanics here. So I just felt that, okay, let's just have a kind of very, very quick look at one particular aspect. For example, we would know that when it comes, it is an isotopic material, we have got two elastic constants, independent, E, Z, and nu, out of the these three, any two are independent. Whereas in the case of composites, this number can be actually 81, but under a number of assumptions or simplifying criteria, this number can progressively be reduced to 36, then 21, then 9, then 5, and finally 4 for a plane stress conditions where we have got E1, E2, Z12, and U12. And these four parameters, elastic constants, would actually define a lamina or a single ply in our mechanics, the laminated composites mechanics. And again, when we would discuss the mechanics of a composite structure, we can look at it at two angles. On the left side, the levels in the building blocks of a composite structure, and what are the different levels in the study. Okay, now, as we know, any composite structure, a composite material, is composed of reinforcement and matrix, the constituents basically. Now, at this level, the study or analysis, whatever we would say, is basically experimental. And the next level is the lamina or the individual ply. At this level, or at here, the study is either experimental work on the lamina or micromechanical studies. That's where we'll come across terms like micromechanics of lamina and things like that. Here, at this micro level or micromechanics, we would actually look at the interaction between the resin and the matrix and the reinforcement. And a lamina can also be studied at a macro level where the lamina is considered, as I had shown in the previous slide. A lamina is considered or represented only in terms of those four parameters: E1, E2, Z12, and U. And finally, when it comes to a final product that is composed of a few laminates, joints, and composite structure, here the analysis is essentially at a macro level. So we have got macromechanical analysis and analysis of the joints and analysis of the overall composite structures. And this particular definition or the framework I've just tried to show in the form of a triangle. Let's look at it a little bit more in detail. At the base of this triangle, we have got the constituents, the fibers and resin. As I told before, the study is essentially experimental. Next level is the lamina or the laminae, where the study is experimental, micromechanical, or macromechanical. Then, by combining a few laminae, we get a laminate. At this level, the study is essentially macromechanical. Then, finally, we get the full-scale product, where the study is essentially experimental, or we can do studies or analysis by means of FE and things like that. In between, we have got two more things: the elemental level study and subscale study. Elemental level study can be, for example, if you consider a kind of laminate that has got some cutout, or a laminate where there is some particular provision for some bracket or things like that, then the standard macromechanical analysis tools may not be applicable. There we have to do some sort of, we have to devise some sort of elements, okay, specialized shape configuration of that particular part, and we study mostly with experimental work or by finite element. Similarly, a subscale component can be actually the full scale component, the entire thing, but the final product, but to a smaller scale, and there also the work is basically experimental and finite elements. Well, I'm sure those who are into composites, they will be knowing what CLT means, classical laminar theory. That's what it is. And this is one particular point or particular topic that is there in the center of mechanics of composites, especially laminated composites. But here I would like to make another point, is that most people in composites industry, especially those who are in the shop floor, would consider mechanics of composite as a complex subject. Now, I made a point in the very beginning that classification, Okay. Now, first we should know where we stand. Okay. And after we know that we are in the laminated composites group, and then we are in this classical laminatory, the overall procedure is something like this. We start at the mechanical properties like E1, E2, Z12, and nu12. That is the longitudinal modulus along the fiber direction, that is the transverse modulus, that is across the fibers, the in-plane shear modulus, and in-plane Poisson's ratio. These four parameters, these four stiffness parameters would define the lamina, and this is basically for the material. And these four parameters would form the Q matrix, that is referred to as the reduced stiffness matrix. Note that this particular matrix is for the material. Then, as we had seen before, by combining a few laminae in different directions, we get a laminate. Okay. And a lamina and a laminate can be in different orientations, different angles theta. And by bringing in theta, we get a matrix called Q bar. This is called lamina transformed reduced stiffness matrix. This is the second level. And from this lamina matrix, for a laminate, we'll have a number of Q bar matrices. For each lamina, there will basically be one Q bar matrix. From all these, what we can get are these A, B, B, D matrices, where these are the laminate stiffness and compliance matrices for A star, B star, C star, and D star. I'm not going to go into this, but here, what is brought in here is the Z coordinate, that is the thickness directional parameters of the laminate are also brought into it, and what we get are these laminate stiffness matrices. And by combining the load vectors and the laminate stiffness matrices, we can obtain the laminate mid-plane strains and curvatures, and from the in-plane or mid-plane strains, we get the global stress strains. From there, we can get the local strains and the global stresses and local stresses. These local stresses and the local strains are used in some lamina failure criteria, and based on which we finally say whether our laminate is safe or not. This is in very brief how classical laminate theory would work. Quite obviously, I have not addressed these parameters in detail, so it might sound a little bit of too much for those who would not possibly know what CLT is. But my only point is that if we go by a step by, or if we follow a kind of step-by-step procedure the way I have just defined or addressed, then mechanics is not really very difficult. Well, finite element analysis, I'm sure everybody would know, but I just felt that we should remember a few points. First of all, finite element modeling of composites is not design of composites. This is a kind. This is mostly. I have come across many people, many professionals, many students who would say, whenever I would ask, "Can we do a design?" Straight away, the design would, quote unquote, the design would actually move to the analysis. There is a basic difference. There are a number of points between that can be cited as the difference between design and analysis. I'm not going to go into those things, but let us not note here that there are a few or several FE packages like ANSYS, Abacus, Nastran, NISA, etc. These packages are definitely helpful, but we must know what is going on when you do some analysis by using these packages. But because we must remember what GIGO stands for, unless we know what these softwares or what these packages do, then we would not really know what output we have got. And in the case of composites modeling, these particular areas must be taken care of. Anisotropic material properties, composites are anisotropic, we must remember that. Stacking sequence is very important. As we know, in a laminate, there are a number of laminae or number of plies. They are arranged in different orientations. If we do not take care of the orientations, that is Q bar. Remember Q bar. Q bar is different from Q matrix. If we do not take that into account, then we are bound to get some wrong answers Again, GIGO, care for orientations, as I just mentioned, and boundary conditions that is applicable to any structural analysis, whether it is composites or any isotropic materials. In any case, it would be applicable. Now, output is another part. Okay, in any composites, for anything we will get stress and strain, but in composite stress and strain, this data would be different in different plies. In each ply will have its own stress distribution, strain distribution. So accordingly, different plies can fail at different times according to what we have got terms like first ply failure or last ply failure. Laminate, for that matter, a structure can be defined when the first ply fails or when the last ply fails, or for that matter, as a designer, you can also decide or you can also define your failure is when a particular ply fails. And in this, we will get actually a lot of data. We must know that we should not get lost. We must know the basics, and the basis or basic procedures in FE also we must know. Here, it is important, as I was just trying to say, the analysis of analysis results, that is, we get, whenever we do any analysis, especially with composites, we get a deluge of information, a lot of data, stress data in each ply at different locations, strain data in each ply in different locations for in a structural analysis, in the case of thermal analysis, temperature distribution, so on and so forth. Now, how do we take care of this data and come to a conclusion or whatever we would like to conclude? There is a possibility that we can employ AI to find some pattern in the data output, and possibly we can do analysis in a more fruitful way, more meaningful way. Well, how do we go about? Mechanics of composites is complex. Normally, that's what is perceived, and to some extent, it is true because of the anisotropy nature of it. Large number of elastic constants. It can be 81 if it is, totally anisotropic, but otherwise it can be brought down to 36, 21, as I had just said before, 9, or finally 4 numbers. In spite of that, there are more numbers. Okay. Then large amount of output data is always created, and idealizations. There are idealizations where, and we have got assumptions and restrictions in respect of plane stress, plane strain conditions. Material idealizations, remember constitutive relations that are actually obtained by experimentation. Okay, and there are assumptions and restrictions in classical laminar theory. Are these all valid? Okay, now there is a possibility that AI can help us arrive at or develop some more realistic constitutive model, and accordingly we should be able to do more innovative idealization and get more realistic and efficient analysis of composite structures. The third domain in composite technology is in respect of manufacturing. Composite manufacturing is different from metal manufacturing. It is by definition a process of material addition, unlike in metal where it is a process of material removal. And there are different processes that can be broadly classified into 3 groups. By the way, this is only for the sake of discussion, for convenience. Okay. First one is open mold processes, where you have got wet layup, pre-preg layup, spray up, rosette layup, etc. Then in this processes, what are some like, you have a mold or a kind of metallic plate or some other material hardware on which you do a layup. Basically, one side of the mold is open, and that's why it is referred to as open mold process. Whereas in the case of closed mold processes, there also we use a mold, but there will essentially be at least 2 halves, or it will be a kind of closed cavity will be formed inside a mold where the composite is formed within that cavity. And there we have got the compression molding, resin transfer molding, etc. with a number of variants. Then we have got continuous molding processes like filament winding, pulcrusion, tape winding, fiber placement, etc. Well, irrespective of whichever method that we would consider or we would possibly be interested in or we would be using for any composite product development, or there are basically four basic steps that are always there in any composite processing. They are impregnation, layup, consolidation, and solidification. Note that these four processes or four steps will have to be there necessarily in any manufacturing method in composite, but the way we would implement would actually depend on the particular method, and the sequence also can be different. But let us know what these four steps are. First one is impregnation. This is a process where basically each and every filament in the reinforcement or reinforced filament basically are wetted by the resin. The next one is layup. It corresponds to orientation. Basically, the reinforcements, the wetted reinforcements have to be placed in their respective orientations. That is basically it concerns the layup. And third one is the consolidation. In this step, basically we ensure that excess resin or if there is an air gap, etc., those things will have to be removed so that there is intimate contact between the wetted fabrics or wetted filaments. And finally, a composite is composite takes but when the resin solidifies. After all, the resin, when we actually make a composite product, would actually be basically when we are doing impregnation, resin is in a liquid state, and resin has to solidify. It is mostly referred to as curing, during which the resin goes through undergoes some sort of cross-linking. Small polymer molecules in a monomer would cross-link and become large molecules, forming a very complex three-dimensional network of large molecules, and that resin cures, and thereby the composite gets its own solid shape. As I had said, these are all essential steps, but the methodology and exact order of implementation would actually depend on the manufacturing method and physical forms of the reinforcement as well as that of the matrix. Let us have a look at the various things quickly. For example, wet layup. As you can see here, there is a mold. This is one-sided, so that's why it is open layup. We are basically going on placing the fabrics, dry reinforcement or wetted reinforcement, and we are placing them. Okay, this is how a layup goes. And mind you, there are a number of advantages or disadvantages. It is a simple process. It needs very, very low capital investment, but this process is very highly labor intensive. Part quality is not up to the mark normally. Well, sorry. Yeah. Part quality is often normally dependent on the individual skill, and process is somewhat messy. A number of items are being applications used. For example, boards, windmill blades. For example, you can use a kind of loft template technique for making blades, swimming pool, storage tanks, so on and so forth. Then pre-preg, here the impregnation of the fabric would take place earlier before we actually go to the shop floor, and the resin in the reinforcement would actually be advanced to a stage called B stage, where it becomes easily usable and stored in a cold storage and used in this particular way. And it is cured mostly under vacuum in an autoclave, where we apply temperature, high temperature. We also apply positive pressure and negative pressure, that is vacuum. And again, this is also an open mold process. This is very, very, it can actually give rise to very, very good product. For example, aircraft wings would use, radomes, sporting goods, etc. But this process has got some disadvantages. For example, it is very, very expensive, especially the autoclave consumables are normally very expensive. Autoclave by itself is also a very expensive equipment. Then compression molding is a closed mold process. As you can see here, there is a mold at the bottom, there is a mold at the top, And when you close the mold, in between there is a kind of cavity. This cavity actually is basically corresponds to the it corresponds to the part. The part shape is obtained by from the mold, and this process. I mean, you can or you can actually do with the help of some molds. Okay, there are advantages, there are disadvantages. I'm sure. Okay, you will get these points. And in automotive sector, this is a very common method. Okay, in housing sector also, doors, windows, etc. are made. Launch vehicles, some control fins, nozzle liners, etc. are made by this method. I just mentioned there is something called preform. Preform can be used in resin transfer molding, where a dry three-dimensional shape of the product is placed in a closed mold, as shown in this figure, and resin is transferred or infiltrated into the preform, and we get the final product, something like this. Okay, we can make near net shape products, and there are other advantages like, okay, you can get good surface finish on all around, and it is investment also can be low initially, but tool design is normally very complex and process modeling is required. Okay. Many parts are basically made by using this modeling process. Pultrusion is a continuous molding process wherein the fibers are drawn through a resin butt and made to pass through a heated die, and in the process it gets cured in line, and the part is continuously produced and cut to shapes as shown in the figure. But it is a very fast process. It can be highly automated, but one of the great disadvantages is that the cross sectional of these parts are mostly constant. Okay, and it is good for making beams, channels, etc. And various profiles for house construction, for example, window panel, door panel, etc., can be made by this process. Yes, I will spend some time on filament winding. This is another continuous molding processes. Okay, usually this is used for making parts like pressure vessels like hydrogen storage tank, rocket motor casings, pipes, storage tanks, etc., etc. And here it is something like this. You can see here there are some spools here. Here we actually load the unidirectional fibers, for example, roving or tows, and these rovings or tows are actually pulled through a resin butt as shown over here, and by it is deposited on a mandrel, a rotating mandrel, by a payout eye. Let us have a look how the four basic steps are implemented in filament winding. Impregnation can be either wet or wet, re-roll and dry. Let us just look at wet. In this resin butt, the fibers get wetted. That's where impregnation takes place. Layup. In layup, basically, we are bothered about with the orientation. The mandrel is rotated, and when the mandrel is rotated, the payout eye or the fiber depositing head also moves along the length and across the length, and also it can rotate. Basically, a number of axis of motions are involved, and by simultaneously controlling these axis of motions, we can deposit the fibers in different orientations, and accordingly we can get three basic patterns of hook winding, helical winding, and polar winding. Hook winding is winding along a circumferential round. Basically, helical winding is along a helix, polar winding is along a plane. Okay, now solidification, that is curing, can be in an oven, that is at room temperature. It can be at elevated or high temperatures and so on. You can use electron beam curing or ultraviolet ray curing, etc. Mostly, okay, we do at room temperature or at elevated temperature in oven. And consolidation. In filament winding, mostly no consolidation pressure is required. The winding is done under some pressure, under some tension. And because of the tension and because of the radius of gyration over the radius of curvature at the local point of contact, a kind of consolidation pressure is created that itself is sufficient for removal of excess resin and air pockets. So accordingly, as we can see here, these are the four basic steps that are getting implemented in filament winding. Let's look at how hook winding is done. In the schematic, as you can see here, the mandrel is made to rotate here, and as it goes, the filaments, the weighted filaments here are getting deposited. By the way, it's a very, very simplistic simulation by PowerPoint. Okay, it is only for illustration of the process. Certain winding programs reason is a very, very simple winding program. It normally would involve only two axes, as you can see here, the rotation, that is C, and the translation of the peyote along the axis of the mandrel, that is Z. Other axes like X, A are basically all zero. Okay. Well, can AI play some role in hook winding? Imagine while doing hook winding, some filaments break. Instead of stopping the machine, can AI take some corrective action only to change the winding program in real time and we continue? This is for innovation. Now, helical winding, as I had just mentioned, that it is along a helix. As you can see here, this is helical winding that is going on. The mandrel is made to rotate. Now, here probably you'll be able to see only the axis is going in this direction moving, but this peyote also actually rotates, and the peyote can actually move across the normal to the mandrel axis. So this is the forward pass that is happening, then it takes a reversal from the other end, that is a reverse pass, as you would see just now. Okay, this is a reverse pass, and a winding program can actually have a number of blocks. A typical block here is shown here. As you can see here, this X, Z, A, C, these are all non-zero. That means different axis of motions come in the picture. It forms some sort of studs like this, and what we get is a kind of double ply construction, and the angle of winding, which is defined over here, is a major parameter in the design of any helically wound structure. Once again, AI can play some role, a very important role in fiber path deviation. For example, let's say while winding the path, for whatever reason, basically due to physical reasons, if the fibers get deviated from the desired path, can we modify the path or program so that we take care of the, or basically we correct the winding? Advantages and disadvantages are also there, definitely, in filament winding. One of the most important parameters to consider, advantages here, is that no consolidation pressure is required in filament winding in general. So autoclave is not really necessary. It can be highly automated. Fibers can be placed accurately by filament winding, and other parameters anyway there. But amongst the disadvantages, it is not suitable for concave outward parts, and fiber volume fraction can sometimes be low. There are other aspects in any composite processing, for example, filament winding too, regarding tooling and processing. The tool that is used in filament winding is basically a mandrel. A mandrel can be of different types. It can be integral, collapsible, inflatable, lost mandrel, etc. And mandrel design, mandrel materials, all these parameters do come into picture. Okay. For example, if I just ask, of course, for example, let's say we are designing a hydrogen storage tank, a CNG cylinder, or some pressure vessel. Quite obviously, the openings would be small, but the main mandrel would be much larger. After winding, the mandrel has to come out through the small opening. How do we make it happen? Those aspects actually will have to be addressed while designing a mandrel. Next comes a major question. Okay, how do we select a particular manufacturing process for a particular application? Let's say I'm designing again a hydrogen storage tank, or let's say I'm designing a wing for an aircraft, or I'm designing a utility pole for electricity distribution, and so on and so forth. Okay. Which particular process we should select? Okay, this process selection can basically be addressed from two angles: the parameters related to the product and parameters related to the process. That again can be the very basic description of the product or product requirements. Some product actually require some particular applications. They need something from the process. Okay. For example, some product may demand high surface finish or good surface finish on both the surfaces. If that be the case, filament winding probably may not be the best route. Similarly, hand layup can open layup, whatever we have seen in the very first place, probably will not be good if we need good surface finish on both the surfaces. Uh, Similarly, there are other parameters that are related to the process requirements. Some processes need or demand very high, investment in the facilities, whereas some others do not. For example, layup needs very low investment. We hardly need a small mandrel or small layup tool, mostly in room temperature. Hardly any requirement of other facilities, whereas autoclave probably might need very sophisticated tools or equipment. Okay. Similarly, process characteristics. Some processes are highly automated, for example, filament winding, whereas others, for example, resin transfer molding may not necessarily be. Yes, another point is there. Although there are so many processes and so many parameters to be considered, but luckily, for various processes and for various applications, many manufacturing processes go as a default choice. For example, if you are designing a pressure vessel, probably filament winding is the default choice. If you are designing a wing for an aircraft, maybe pre-preg layup would be the default choice, and so on. In composite manufacturing too, there are many innovations that can happen, and some of those innovations can be automation, etc. But one thing what we can probably bring in is application of AI. Process design. In composites, the structural design itself is not adequate. We have to do a lot of process design. The structural design would say that there should be 5 layers, 10 layers, 20 layers at different angles. But when it comes to process design, we actually have to say what would be the size and shape of each and every development, which development has to come at what instant in time. Okay, and what should be the kind of overlap between two sheets? Then how do we model this? And uh, AI can actually help in this kind of process design and modeling and process monitoring. Again, let us go back to our filament winding. Let's say when we are doing filament winding, the resin viscosity has to be maintained at some particular range. Temperature has to be maintained. Then filament tension has to be maintained. All these parameters are monitored mostly manually. Now, we can possibly automate them, but at the same time, we can possibly not only automate but also monitor them with the help of some AI-assisted system. Accordingly, whenever there is any deviation, AI system possibly can take corrective action and control accordingly. And accordingly, the reliability and quality assurance in manufacturing can be improved. And when it comes, we proceed or we graduate from development to production. In a production environment, there are many more parameters to be looked at, and that production management can be controlled, can be overseen by AI. So on and so forth. We have got many areas where AI possibly can help. The fourth area or domain is testing and composites. Let us know the objectives. Tests are carried out basically for 3 reasons with 3 goals. First one is design and analysis. During any design of any product and analysis, we need material data. This data has to come from testing. Then in any product realization or product development cycle or product manufacturing, quality control and quality assurance, QC and QA, play a major role. And in QC and QA, too, testings play a major role. We have to know what material, the incoming material has to be cleared, that is by testing. Once the product is made, we have to test it to see whether it is acceptable or not, whether it can withstand the desired loads or not. Okay. And the third area is in respect of research and development. For developing some new materials, for example, we have to carry out tests. Those test data will also come, the data also will again come from tests. And let us also note that tests can be done on the material or on the product, and tests can be either destructive or non-destructive, and tests are done at different levels. Let us recall that triangle that we have shown in the case of mechanics. Similar triangle can be considered, and based on that, we have got constituent level tests, basically on the fibers and resin. Let us recall at this level, the study is essentially experimental. So we carry out tests on the fibers and on the resin. Then next level, again, let us recall, is at the level of lamina. At the level of lamina, the tests can be either experimental, study can be either experimental or micro level or macro. Now, when it is experimental, we have to carry out tests like non-mechanical parameters like density, mechanical parameters, and so forth. Next level after lamina is laminate. There also the same parameters are required to be tested. Then you would remember I talked about element level tests. There we test joints, laminate with holes, etc. And finally, subscale component and full scale component. There we carry out tests like pressure vessel, a pressure test or load test, fatigue test, etc. And there are also non-destructive tests like ultrasonic examination, X-ray delivery, acoustic emission, etc. And this is the building block that I was referring to. You can just note here at the bottom we have got a constituent level test from fibers. Finally, we go and resin, we go all the way to the full scale. At the bottom level, we have got simple tests, but many. These are predominantly destructive. And as you go up the triangle, the number of tests come down. Okay, at the top, we may have only one or two tests, but the complexity increases. And at this level, the tests can be destructive or non-destructive both. Non-destructive testing, by definition, they do not destroy the product or they do not cause damage to the part. And we carry out non-destructive testing mainly for identifying or detecting defects. There can be one more dimension to it. I'll just come to it. I have not shown here. Why I have just chosen to show these defects. On many occasions from experience, I have found that people would confuse in referring to these defects. Defects can be in respect of the fibers, fiber breakage, non-uniform fiber distribution, etc. Defects can be in the matrix. There can be some foreign object, some contaminations, porosity, etc., matrix cracking. Then defects can be there in the fiber matrix interface, delaminations. And there can be other defects like D-bonds. The terms delaminations and D-bonds are mostly confused by most people. And there can be one more application of non-destructive testing, that is for evaluation of material properties at a product level, which is an area that is slowly getting more or attracting more and more importance. Well, what can we do in testing with the help of AI? Data interpretation, for example, let's say we have done some radiography. Okay, we have got some radiography, radiograph films. I'm sure everybody would know what a radiography is. Now, how do we interpret a radiograph? Or let's say we have done some ultrasonic examination. How do we interpret the data? AI can actually help us, and AI can be, for example, a machine learning based model can be trained, and it can consistently interpret films or the acoustic emission or UT readings consistently and correctly. Non-destructive evaluation of material, as I was just mentioning in the previous slide, AI can actually help in the non-destructive examination of a material at a product level. Actually, this particular point I have mentioned in the beginning also. Material properties can be, whatever material properties we would use in our design and analysis are basically samples. But how do we know that the same material properties are actually valid in the final product? Because material in composition in particular, the product or the material is created during processing. If the processing methodology is not exactly the same, the conditions are not exactly the same, which is normally the case, from the conditions of making the samples, then it is very unlikely that the material properties would be the same in the product as they were in the sample. So there is a requirement, there is a need that we know the material properties at a product level. Non-destructive testing assisted by AI can do or fill this gap. Then we can also do some sort of virtual testing with the help of some digital twin in product acceptance. There are other areas that we can think of where AI can possibly help us in testing. We have gone through all the four domains in composite product design. Okay, then finally we need to look at the very area of product design. And what is design? We all know it is basically a process where we have a requirement, we have some resources, and we have under some constraints, we get a solution to meet the final requirements. Okay, I'm not going to elaborate on these things, but just a query. Can artificial intelligence be considered or can be used as a resource in design? Well, someone said that it cannot be a resource, it is actually a partner. Well, whichever way you consider, can artificial or AI be used in product design? Let us now again, product design is not exactly a particular streamlined process that follows any particular sequence. As we mentioned before, it has got materials, manufacturing, testing, mechanics and analysis. All these areas are interconnected in the design domain, but our thought process goes or works in a better way if we arrange them in some sort of steps. So I feel comfortable if we just place them in the 7 steps. Generation of specifications. See, whenever we have to design any product, first what we need are the specifications. Generation of specification is first step, but mind you, this is not a one-way traffic. It is not in any one way. It's not that the customer says, this is what my requirements are, and these are the specifications. No. In most cases, the specification will have to be arrived at through a number of iterations. Okay, across the table, we have to discuss and say, and finally come to a common ground that these are the final specifications. As a matter of fact, sometimes during the process of evolution or development of the product, also specifications get modified. The next step is material selection. In the case of composites, okay, let us recall the materials are of 4 different types: metal, ceramics, polymers, and composites. Now that we are talking about composites, obviously we are discussing only composite material. Now, while selecting a composite material, also we have to make a number of decisions. Let us note that design is a process of making decisions, making some selections. And when we select materials in composites, we have to select the resin, we have to select the reinforcement. And when we select the resin, okay, then there are subtypes. Okay, in epoxy also there are 1,000 varieties. We have to choose which exact variety which we have to choose. Sometimes the resin may have to be developed specifically for a particular product. Then we have to choose the reinforcement. It can be either carbon, glass, Kevlar, or aramid, and so on. In carbon also you have got pan-based carbon fiber, pitch, or rayon-based, and so on. Again, in pan, there are different types of carbon fibers: high modulus, intermediate modulus, high strength, so on. Okay. And their physical form. It can be a roving, it can be a tow, it can be a strand, or it can be yarn, it can be fabric, and so on. Okay. That is what we do in material selection. The configuration design, it is associated with the shape and size of the product. I'll just address this one and a little later. The manufacturing process selection, this part we have addressed a little while ago. This is another point that has to be definitely considered in product design. The testing and ND options. Okay, this is important because if we do not pay adequate attention to this testing and ND options in the beginning of the design process, if we make a product and finally we are not able to do any NDE, non-destructive evaluation of the product, and say that it does not have any defect or it is usable, then its acceptance is doubtful. Then design of parts, especially the laminate and the joints. Why okay, and finally analysis. I actually would like to address this configuration and laminates. Laminate design is something different and it is peculiar to composite design. So we'll just address this particular part a little bit in detail. First, configuration. Well, what we understand by configuration basically is overall shape and the size. What should be the shape of a product? For example, all of us would possibly be sitting inside some room, some hall, whatever. Now, I'm sure these rooms have got some walls. Okay. Why should the place that we are sitting in should be of the shape that whatever they are? Now, that shape and that size, basically they constitute basically the overall configuration or would define the configuration of a product. Okay, and when we do configuration design, we make a selection, we make a choice in regard to the overall shape and size. Then any structure is again made up of a few basic structural elements. There can be some beams, there can be some shells or plates and things like that. Okay, we again choose what these basic elements will be. For example, if you're talking about say a utility pole, it can be a long pipe kind of structure. Maybe it is a shell, a long shell. There will be some other elements like some adapters, okay, or maybe some cutout and with some reinforcement and so on. The shape and size of each individual structural element also will have to be chosen during configuration design. And finally, proper joints. Joints are normally the weak links in a structure, and proper configuration of the joints is an essential aspect of configuration design. And here, let us note that current state of the art is that primarily configuration design is based on engineering judgment. As I was just referring to our own room or buildings that we are sitting in right now, they are definitely designed based on past experience and some engineering judgment. Okay, now there will have to be some innovation. Why should the room be cubical the way they are? Why should the walls be mostly flat and straight? Okay, why are they not in the shape of some shell? Okay, maybe some other shape would be more optimal or more efficient. And when we consider this kind of configuration, the options available in front of us are infinite. And AI possibly can help us making a right choice in this direction. Laminate design, the ply sequencing is a central concept in composite laminated composite product design. Laminate, here there are three areas: laminate selection, analysis and measurement, and finally design criteria. Okay, laminate selection is basically what kind of plies we have to have, what orientations, etc. But unfortunately, the starting point is somewhat arbitrary. And what we do here are mainly three aspects in the selection of any stacking sequence. We choose the material of each ply. It may be carbon epoxy, it can be glass polyester, it can be Kevlar epoxy, or so on and so forth. The ply, the material for one ply need not necessarily be the same in the other one. It can be different from each other, and only thing compatibility will have to be seen. The thickness of each ply and their orientation. Okay, these are the basic things, three things that we have to choose. But again, the starting point is actually arbitrary. Even if we have chosen the material and what should be the thickness of each ply and what should be the orientation, we have got practically infinite options. For example, the orientation, it can be from 0 to 90 degrees. Okay, but between 0 and 90 for each ply, we have got infinite options, and we have got infinite options for the number each ply. So accordingly, we have got practically innumerable infinite solutions. Now, which is the best one? We do not know. So mostly what is done is the design is started with some starting point with some arbitrary figures. Maybe we would choose some angle like 45 degrees, 30 degrees, 60 degrees, etc., and carry out studies, do analysis, and finally come to a conclusion in respect of a practically optimal solution, which need not necessarily be, by the way, always the best solution. Then, once we have made some selection of the laminate, the ply sequence or stacking sequence, now we need to carry out some analysis or some studies. Okay. Now, there are two things: analysis and measurement. Let us address first analysis. For analysis, we have got finite element model, classical laminate theory, netting model, etc. What do we do by these tools? Is basically we find out some parameters like the stresses and strains at different locations, displacements, the temperature distribution, the natural frequency, mode shape, etc. Okay. For these parameters, these analysis tools are helpful, but not all parameters can be analyzed and found out. There are some parameters that need to be found out only by measurement or by experimentation. For example, fatigue life, impact characteristics, or ablative response, and things like that. But in any case, after this particular phase, what we get are basically these parameters like displacement or stress or strain. But what do we do with these parameters? Based on these parameters, we have to finally make a conclusion whether our laminate is safe or not under the applied loads. Then we bring in some design criteria like the strength-based criteria, stiffness-based criteria, etc. And let us bring in the concepts of the failure criteria. In metal, the failure criteria are the principal stress, principal strain, etc. In composites, these criteria are in respect of strength, maximum stress criterion; in respect of stiffness, maximum strain criterion; and there are other criteria like Psi-Hill criterion or Psi-Hu criterion, and so on. Similarly, for fatigue life, energy absorption, etc., we, based on the measurement, whatever value we would get, we would apply these things in our acceptance limit, and then come to a conclusion whether our chosen laminate is safe or not, or acceptable or not for the given loads. This is a kind of chart which can be applied for making a decision whether a laminate is safe or not. As I had just mentioned, initial laminate selection is somewhat arbitrary, but we make a selection for the given part configuration, the applied loads, materials, and processes, then carry out analysis and measurement, then find out the output will be number of plies, ply thickness, materials orientation. Then we find out the stress distribution, deflections, etc. Then we apply them in this design criteria check. Then apply this, check within limit or not. Then either no or yes. If it is yes, very good. If it is no, then we repeat the process. And mind you, this becomes a kind of iterative process. And because of the iteration, there can be n number of iterations, but again, practically this number of iterations will have to be limited when we do manually. Again, if we have got some sort of automated system controlled or based on AI, this process can be automated and can be improved, and we would be able to get much better solution. This is what I am just trying to show here. Configuration design, AI can help us. Ply design, we can bring in optimality by AI. Composite mechanics and analysis. Remember, we had talked about the constitutive relations based on experimentation. There probably we can develop some more innovative and optimal or more realistic constitutive relations. I would like to conclude now with these broad two aspects. In composites, in mechanical engineering, okay, we can work in closed compartments if we wish to, in specialized fields. But if we have to work in a real life structure, it has to be a kind of integrated approach covering materials, mechanics and analysis, manufacturing and testing, as shown in this thing, which is essential for successful product development. And for composites in next generation of mechanical engineering, exciting opportunities definitely exist in the domain areas that we mentioned. AI can play a crucial role. I have only given a few possibilities. There are plenty of more possibilities that exist. Well, most of the things that I have present today are basically borrowed from my book. If anyone wishes to know more, it is available. Thank you so much. We are open for some discussions.
Hello.
Sorry, no one is audible.
Hello.
Yeah, I can hear you now.
Sir, it's basically a wonderful session, sir. So can
Yeah.
I take up on the questions from the participants?
Yes, yes, please. Hello.
Dear participants, any questions? Yes. Hello. Am I audible, sir?
Sorry, no one is audible.
Hello.
Yeah, I can hear you now. Yes. Okay.
Sir, this was really a wonderful session, sir. So can I take up on the questions from the participants?
Yeah, yeah, please.
Dear participants, any questions you can freely ask. The Mano sir is ready.
Looks like everybody understood everything or nobody understood anything.
Can you give some few suggestions on mathematical modeling techniques?
Looks like everybody understood everything or nobody understood anything.
Can you give some few suggestions on mathematical modeling techniques in predicting the mechanical behavior of the composite laminate or any?
Well, mathematical modeling techniques, they would depend on the kind of structure that you have got. If you are making a structure by filament winding, it would be something. Again, if you are doing it by hand layup, and again, it would depend on the physical forms of the reinforcement. And again, for example, if you are doing some particulate reinforcement modeling of any structure, it would be then we cannot use classical laminate theory. But if you are doing laminated composites by, for example, by layup in, then it would be something else. And similarly, again, carbon and three-dimensional reinforcement, if we use, then the mathematical technique would be something different. So it would actually depend on the kind of structure. Classical laminate theory is useful if you are doing some design or analysis of a pipe or a pressure vessel in the cylindrical region. But if you are doing the again analysis of some structure involving some joints, and there it is going to be not very useful. If you are using CL, it will not be valid. But there probably you can use finite element model and things like that.
Thank you, sir. Shaktivel, sir, please unmute yourself and ask the question, sir. Shaktivel, sir, you raised your hand. You can feel free to ask any questions.
Yeah, I'm sorry, I'm not able to get, I'm not able to hear.
Hello.
Actually, I will always admit one thing. Okay, online forum is actually not very convenient because you do not see the faces, you do not know, you don't get to know whether the participants are with you or not. Okay. And as a matter of fact, I made a mistake in the very beginning. I did not ask anybody what the background was. Okay.
Of mechanical engineering in any point.
At least may I know, okay, from the audience, how many of the audience, I think all the audience is basically faculty members, right? How many of the faculty members are, acquainted with composites?
Yes, sir. Almost each and every faculty of mechanical engineering in any point of time they have heard the name composite, sir.
Oh, then
They have the basic idea.
okay, then it should not be difficult. Okay, I'm sure. Yeah, I can hear you.
So what is the basic difference between the macro mechanical and micro mechanical for the composite material?
Yeah, micromechanics or micromechanical analysis, as we know, that is at the level of lamina, whereas macro mechanics can be either at a lamina level or at a laminate level. In micromechanics, what we do is we basically discuss or we consider the in between. We consider the resin and the fibers or the matrix and the reinforcement. We consider their interactions. Okay, or we consider their presence separately, individually. Whereas at the macro level, we ignore the, we basically do not consider the reinforcement and the matrix. We consider the lamina as the basic starting block, where a lamina is represented by those parameters you would remember: E1, the longitudinal modulus; E2, that is the transverse modulus; the Z12, that is the in-plane shear modulus; and nu12, that is in-plane Poisson's ratio. In micromechanics, E1, E2, etc. will come, but E1 will actually be found out from the stiffness parameters of the reinforcement and that of the matrix. Whereas in macromechanics, the individual fiber or the matrix or the reinforcement and matrix stiffness parameters do not enter. I hope I have made the point clear.
It's clear, sir. Now it's very clear. Thank you.
Okay.
Sir,
Yeah.
actually there are different fabrication methods for fabricating composites.
Yeah.
So, what do you prefer, vacuum bag, resin transfer, or 3D printing? What is better?
Well, 3D printing, I would not comment because that is something I would not consider it as a very regular composite processing technique as of now. Okay. Then you talked about vacuum bagging and resin transfer molding, right?
Yes, sir.
Yeah, okay. Now, whether it is vacuum bagging or resin transfer molding, see, vacuum bagging is not exactly a processing technique. It is used for during curing. Okay, during curing, especially in pre-preg layer. Okay. Now, let me first talk about resin transfer molding. In resin transfer molding, what we do is we take a preform, mostly a three-dimensional preform. It can be two-dimensional preform as well that can be arranged in 3D. And we place the preform in a closed mold. Okay. The cavity will give the shape of the product, and through the reinforcement, through the preform,
ఆయన కూడా మ్యూట్ చేశారు. ఆయన ఎత్తకండి ఇక్కడ. వచ్చింది చూడండి. హలో సార్. సార్. Hello.
Am I audible now?
Yeah. You're audible, sir. Yeah.
Sorry, it got muted on its own. I don't know what happened.
Sir.
Should I repeat the point? You asked about resin transfer molding and vacuum bagging, right?
Yes, sir.
Okay. What I was saying, see, resin transfer molding is a process where you use a preform. The preform is nothing but some reinforcement arranged in the form of the final product. Okay, or it can be two-dimensional, that is kept inside or a mold, a closed cavity, and a resin is injected into it. As a result, what you get is good surface finish, near net shape product. Okay. And
Yes.
it can be very complex, but process modeling is required. Otherwise, resin will not flow uniformly into the cavity, and you may get a lot of areas with resin-starved pockets will be there. Okay, that is one aspect in very brief. Whereas when you use vacuum bagging by itself is not exactly a composite processing method. It is a part of curing.
Okay.
It is mostly used in pre-preg layer. In pre-preg layer, you use pre-preg sheets layer on a mold. it's an open mold process. Then finally, during cure, for application of consolidation pressure, you apply a vacuum, and when you apply vacuum, you have to have a vacuum bag. The vacuum bag will ensure there is vacuum, and it would remove any porosity or any byproducts, etc. And positive pressure will be effective. That's how you do. But finally, the outside finish, surface finish need not necessarily be very, very good unless you use some other special techniques. And mostly, autoclave curing will be involved. Autoclave will be required whenever you have vacuum bagging, but mostly, not necessarily always. Okay, so they are used in different areas. Okay, different applications. I mean, depending on the product requirement and things like that, as I was telling. And you also asked about 3D printing. 3D printing is not exactly a very common composite processing method. 3D printing can be used in metal, it can be used in composite as well, but in composites, it has not taken the kind of shape probably we would expect. Okay. It has not gone to that level as of now.
Okay, sir. There is one more question, like what are the current better or good techniques that are used for fabrication of composites? And the second point is, if you want to check for delamination of a composite under loading, okay, what are the different equipments that we have physically available to do so?
Okay, let me address these two things in a different way, one by one. First, which composite processing technique? See, what the processing techniques that I just narrated, those are the ones normally will be available even now. Okay, filament winding, pultrusion, fiber placement, etc. in the continuous molding processes, hand layup, pre-preg layup, okay, compression molding, etc. are the molding processes. Okay, either open molding or closed molding. Now, there is nothing called the best process, okay, which is, best, or which is the best across all. Now, see, if you are making a product which does not need a very high sophistication, then hand layup is the best one because it is cheap. But if you want to make a high-end product, okay, an utility pole, for example, or you want to make a hydrogen storage tank, and in hydrogen storage tank, if you want to use resin transfer molding, it may not give you the best thing. For a hydrogen storage tank, right now, the default process is filament winding. Now, from filament winding, probably you can move on to fiber placement, but probably you will not go to resin transfer molding, or you will not go to pre-preg layup. So those manufacturing process selection parameters, okay, those parameters should be considered while making a detailed choice. But again, as I was telling you, these choices normally would go as a default choice. If you are making a bathtub, for example, there you don't do pre-preg layup. Why do you have to spend so much in making a commercial item like a bathtub? There, spray layup is more than sufficient, isn't it? That is the, those are the points of consideration when you design and design. And when you make a choice of the manufacturing process in as a part of product design. Now, the next thing is how do you find out or what are the equipment for delamination detection? Well, delamination will be necessarily there in layered composites. There are different techniques. Okay. Most common technique is ultrasonic examination, okay. And the other one is X-radiography. If you want to find out if any delamination is getting created under loading, then acoustic emission is another one that you actually have to apply some load. But without the presence of any loading, if you want to see, then ultrasonic examination has been very, very popular. Then you have got different variants of ultrasonic testing. You have got A scan, B scan, C scan, then you have got pulse echo, the true transmission, then you have got acousto-ultrasonic. Then some more new techniques are getting popular. I would not say that these techniques are really new. They have come into existence some time ago, but they are getting popularity now. Are something like this NMR, okay, nuclear resonance method. By the way, the ND is not my domain area, but I would be able to say nuclear resonance method NMR. Then you have got this stereography. Then you have got micro ND, etc., etc. There are many other things that are happening, okay. But irrespective of whatever it is, ultrasonic still is probably the most common technique for finding out or detecting delaminations. But it cannot actually locate precise for that across the thickness where exactly it is there. Okay, mostly it is not so reliable, but by X-ray you can find out the location directly.
Thank you, sir.
Yeah.
Thank you.
Thank you.
Any further questions from the participants? Sir, thank you, sir. Thank you very much.
Thank you so much for calling me, inviting